Hello. Imagine that we encounter a system of differential equations that looks like this. So there are some restrictions, namely we have n unknown functions, y1 through yn, and for each of them we want to get a formula for its derivative, which is very useful, but also practical. In applications, differential equations very often come exactly in this way, so it's not too restrictive. And notice that we do not really care what's happening on the right. There are some expressions that feature the unknown functions, and also the independent variable, we call it t, not x, and this will come handy later on. The obvious interpretation is that t is time. It need not to be so, but it's convenient to imagine that it is time. And in particular, if this comes from applications, then most likely this system is not linear, and perhaps it's even unsolvable analytically. And yet, we want to use this system, these differential equations, to gain some understanding of how the process which it describes actually works, because such a system may describe, let's say, some mechanical device, or some structure, or perhaps some process which is happening around us. So we want to see in what possible ways it can develop in time. We want to see what to expect from it. And we asked a question like that before when we had just one differential equation. And we got a big help from a visual representation of solutions. We tried to plot many solutions of different kind into one picture. And then when you look at such a picture, you get a visual feeling for what's really happening in this system. And that's exactly the topic for today's lecture. And let's start with this example. It's a simple 2x2 system, but it's definitely not linear. In the first equation, the unknown function is being squared, and this essentially buries linearity for the system. But even if the first equation were linear, the second equation would spoil it anyway, because here we divide those unknown functions. So this is definitely not a linear system, but it's special. By an extraordinary piece of luck, I know the solutions. For instance, y1 t is e2 negative 2t, y2t is e2 negative t. Now you can check that this is actually a solution. We just substitute it into the formula. You will get it. This is a realistic example, at least we pretend so. So I will use realistic range of validity, t greater than or equal to 0. So that's one solution. And don't ask me how I got it. But the question is, how can I visualize it? Or in general, when I have a system, I get a solution, but now solution means many functions and functions. How do I visualize it? Well, the easiest thing you can do is just plot the graphs, preferably in one picture, so that you can see how they interact, those functions, because they belong together. It's a pair of functions, which is one solution. So let's have a look at it. Here we have a little code. And when I run it, I can see two graphs. The one which is darker, if you can see that, the one which goes steeper down, which we can see over here, e to negative 2x, this function goes to 0 faster than this function. And that's exactly reflected in the graph. The one which is hugging the t-axis more, that's the function y1. And function y2, that's the one which goes in a slower fashion to 0. But they both go to 0. So when I look at a picture like that, I can see quite a lot of things, if I get lucky. So this is definitely a good way to visualize solutions. And if I had a 3x3 system, 4x4, I would have more curves, and I could perhaps see something really useful from it. However, this is not really viable if you want to get overall picture of the behavior, because then you have many solutions, and each solution is a bunch of functions. So when you plot it into a graph, you may get something like this. In this plot, you can see 5 solutions, which means 10 graphs of functions. Now, I used colors to actually encode them so that we can see which functions belong together. So, for instance, we can see, well, really close to the t-axis, we can see the 2 blue curves. That's the previous solution. But I had to scale it so that we can also fit the larger solutions. So, for instance, in the upper half, there are 2 green curves. One is darker, the one which goes down, and one is lighter, the one which goes up, which turns around. And that's another solution. The darker one is y1, the lighter one is y2. So the darker one goes down. Then there is, let's say, in the upper half, we can see a curve which starts at 10, and lower half another curve which starts at -10. They again belong together. The upper one seems to be a little bit darker. Okay, I go with it. It goes to 0, and the later one also goes to 0. That's another nice solution. And we can keep going like that. Notice an interesting solution, which is the one which is in the pink, and it's on the top and also in the lower half. So the function y1 is actually positive, the function y2 is negative, and they go to 0 and they touch the time axis and they disappear. They do not continue anymore. This can happen actually in this system, that the solution disappears. So all kinds of things we can see in this picture, but now just imagine that I add, let's say, 5, 10 more solutions. This is not really manageable. So we need another way to look at solutions. And there is actually a way to simplify the picture, in a way. When we worked with a system like that for linear equations, we actually gained, let's say, help from linear algebra by imagining that we are working with just one function, but it's a vector function. So that's something which hides complications from us. Let's see. In general, the system looks like this. I have a vector of functions, and when I differentiate, I get a vector of functions. These guys, they form a vector with unknown t and y as a vector. So that's the matrix form or a vector form. Rather, there is no matrix now. So vector form of this system. And by the way, if I erase those vector signs, those little arrows, this is exactly a general explicit first-order differential equation that we covered before at the start of this course. So there is a definite similarity. And now when I look at a solution, I see a vector function. And a vector function has just one graph. Let's go back to our previous example, the one with blue curves, 2 blue curves, and let's see how it looks like if I interpret it as a vector function. Here we go. This is the graph. So the horizontal axis, that's t, the independent variable. The axis which goes down and to the left, so it's going against us. It reaches into the classroom. That's y1, and y2 goes upwards. And let's see, how does it look like? That's the curve. You can sort of see how it goes through space. Where does it start? That's a good question. When time is 0, we are starting at position 1, 1. Does it work? Well, let me turn it around like that. And I think that the starting point of this curve really does have coordinates 1 and 1. So this seems to fit. We can also see nicely that as the time goes to infinity, our curve is approaching the origin. So that's also nice. We can see all kinds of things. By the way, if I turn this graph in such a way that y1 as an axis disappears, it goes directly against us, then we can actually see the graph of y2, which is the exponential. And if I turn it so that the axis y2 disappears, then we should see the graph of y1, which is an exponential that goes to the origin faster. And I think it does. So it all makes sense. We actually can recover this individual information from a picture like that, but we do see the whole 3D graph. Now, that's a nice way to visualize. It has several disadvantages, and I will get to them soon, and one of them is obvious. If I didn't have a computer on me, I simply couldn't get anything like that. But this is not all that, let's say, crucial. There will be some more significant disadvantages later on. So now we can visualize solutions. There are curves going through 3D space when you have a 2-dimensional system, 2x2 system. For a 3x3 system, the graph of a solution will be 4-dimensional, which is where it gets interesting. So let's not worry about it yet, okay? Let's stick to 2x2 systems. We can see the graphs. If I imagine the time axis going to the right along the board, then I can see a whole lot of curves going like that in space in some way. I don't know how at this moment, but anyway, we have this nice idea, this visualization, and we talked about a very special kind of a solution when we were doing this analysis of behavior. Some solutions are really interesting. These are the stationary solutions. What does it mean, stationary solution? Again, that's a grand name for something very simple. It's a constant solution. So you have a function which is actually always the same. always the same value, some vector y naught, which is a vector from R to n, in our case, vector from R squared. How does such a solution look like? Well, let's see. Here is the y1, y2 plane, and in this y1, y2 plane, there will be this vector y naught, let's say over here. So this is vector y naught. And now we attach the time axis, and as the time goes, the solution does not change at all. So it is a steel rod which is running parallel to the t-axis. That's how I visualize stationary solutions. You have a system, let's say some mechanical device, and you can set it up in different ways. And that's exactly what's happening at time 0. You set it up in different ways, and then you let it run, and you see how the situation develops. And if you set up the system in this very special way, which is called y naught, then the system likes it and stays that way. So this value y naught is called equilibrium. And again, this is similar to what we did before, for just one equation. Okay, now let's ask a good question. How can I recognize a stationary solution? Well, it's constant. And because it's constant, the derivative must be 0. So we are looking for some value, y naught, but now it's a vector value. That's our question. Can I find some vector, which means values y1 through yn, by the way? So I'm looking at it in two different ways, as a vector problem or as a problem with individual functions. Either way, I'm looking for certain specific n values so that if I put them into my equation, they will give a 0 derivative. So I want f t y naught to be 0, or if you want, I want fi t y01 y0n to be 0. So again, it depends whether I look at individual equations or whether I look at a vector, and I simply want this to be 0, regardless of time. That's important. Now, if my system is autonomous, which is exactly what I expect to have in applications, like this system, there is no independent variable in it, then I get a very simple set of equations. I can solve it for y1 through yn if I get lucky, and I get my stationary solutions. So this is exactly the same way we were doing it before, just we didn't have this arrow symbol over here. We just said fty is 0, that's how we were looking for stationary solutions. Now it is exactly the same game. So let's have a look here. Do I have any stationary solutions? That's a good question. Well. I look at it and I say, well, the first derivative of y1 and the first derivative of y2 should be 0 for any constant solution. So this right-hand side should be 0, and this right-hand side should be 0. Minus 2 y2 squared is 0, and minus y1 over y2 should be 0. Now, from the first equation, it's quite obvious that y2 must be 0. From the second equation, equally obvious, y1 must be 0. So this is our candidate for a stationary solution, but it does not work because when we look at our system, we can see immediately that y2 is not allowed to be 0. That's an important observation. Perhaps we should have started with it because it's a key observation. It's a key limitation of what we can do with solutions. Okay, y2 is not allowed to be 0, which cancels our only candidate for stationary solution. So there is no stationary solution for our example, unfortunately. So we cannot try our tricks on it, which means that we will need another example. Let's have a look at it. Here we go. How did it go? I know. y1 derivative is y2 squared minus 1, and y2 derivative is y2 minus y1. Okay? Now, when I look at the system, I notice that the second equation is linear. The first equation is not. So this is an interesting thing which is happening a lot in differential equations, that you look at two equations or two systems and you compare them visually and you feel that this one looks more friendly because the second equation is linear, which is good. The first equation is actually quite analogous. So you would expect that this system is actually better behaved. But that's not true, because I can find solutions, analytic solutions for this system, but I cannot find them for this one. This one is unsolvable. So it's in fact much harder from theoretical point of view and also from practical point of view. But it's another story. Let's talk about stationary solutions. Well, I want a solution which is constant, so I want the derivative to be 0. So I want y2 squared minus 1 to be 0, and y2 minus y1 to be 0. So this is actually two requirements. y2 squared must be 1, and y1 must be y2. And from the first equation, there are two solutions. And once I get a solution for y2, I immediately get a solution for y1. So there are two stationary solutions. y2 can be 1, and then y1 is automatically also 1 due to the second condition. So this is one stationary solution. But also y2 can be negative 1, and then y1 is also negative 1. So these are my stationary solutions. Now, when I ask about setting up my system so that it works like that, I will talk about equilibria. And there is two of them, 1, 1, and negative 1, negative 1. So that's the settings for my system. And here I can see them as functions, as they develop in time, as solutions. Let's have a look at little visualization. Here we go. So I read my system, I hope it's the right one, y squared minus 1, that fits. I relabeled the unknowns. We will get to it soon, don't worry about it. And here is the picture. Okay, what do I see? I see two straight lines parallel with the time axis, which is exactly the picture that I've been talking about. One of them is located at 1, 1, we can see it over here, and the other at negative 1, negative 1. So that's the two stationary solutions for my system. Very nice. Okay, so finding stationary solutions is usually not such a big problem. And when we go back to, I think, fourth lecture or whatever, when we talk about analyzing solutions for just one ordinary differential equation, we found stationary solutions. And then we asked a good question. Is this stationary solution stable? And that's something which is very important in applications and for the systems as well. So when you find stationary solutions, that's a very important information, but stability, that's perhaps even more important. How do I recognize stable solutions? Well, let's take this idea that we had for one equation and move it to this situation when we are actually talking about the vector solutions. Here, my system behaves in a specific way that it likes. It's just sitting there, not moving. Okay? But now I reach in and I change the setting of the system a little bit. What's going to happen? Let's say that I do it here at this time. For a stable stationary solution, I expect that this little interference, because I interfere with the system, I no longer at that moment was governed by those differential equations. So let's say that I added some extra term, just for a second, some outside force. But then my influence stops, I stopped interfering, and the differential equations, they again come into the play. And they govern the development of the system or of the process. And I'm asking, will I get back to my stationary solution? That's the key question for stability. And if I do, I'm happy. So I'm, let's say, displacing the situation or changing the situation, and I hope that as I'm changing it, I will always get back in the limit to my stationary solution. This is something that I want to see in applications usually. And this is exactly what I need to describe in my formal mathematical definition, but I have to be careful. There are two things I have to worry about. First of all, I cannot really hope that this will work for any displacement. This is a 3D situation, so imagine that I have a rod which is fixed. It's protruding in space, steel rod. I hold it firmly on one end, and now if I displace the other end, then it goes back, of course. You know that. But if I displace it a lot, I simply bend it, I exceed some limitations of material, and it will never go back. So this shows that our expectations have to be a little bit moderated. We are considering displacements, but not too large displacements. There is a neighborhood, but now it's a three-dimensional neighborhood of this curve, of this stationary solution, which means it's like a tube. So there is some radius over here. Let's call it delta. And there is a three-dimensional tube. And I'm only interested in what happens when I displace my situation within this tube. If I displace it more, if I reach into the system and change it a lot, then okay, I don't care what happens. Okay? So that's the first limitation. We will be only interested in displacements like that. And the second limitation is that there could be some moment, some special time when the system behaves, let's say, in an exotic way. But I don't have to worry about it because stability means I'm looking at the development in time reaching to infinity. So if something is happening, let's say, on this part of time axis or on this part, I can simply ignore it. In other words, there will be a cutoff time. I will call it TS. And I'm only interested in what is happening after this time. I don't care about what's happening to the left. That's the past. I don't care. I look into the future. Okay? So these are two important limitations for my investigation. And now I just write it down mathematically. Let's see. Here we have a formal definition. We have a constant solution which solves a system, and you can see it's the general system, the one that we have over here. And we ask for the following condition so that we can say that the solution, the stationary solution, is asymptotically stable. And the condition is there must be some Ts, that's the cutoff time, and there must be some delta, which is the radius of this tube. In other words, that's how far we are allowed to move away from the stationary solutions. And then we demand that whenever we have a solution whose distance from our stationary solution is small enough, which is within the tube, at some time which is after the cutoff, so for instance this solution, this definitely fits, we are looking at time capital T, which is over here, and we moved within the delta. So this solution is one of those that we are testing. And what do we want? We want that this solution must converge to our stationary solution at infinity. So this is what we need for stability, asymptotic stability. And if this does not work, if there are some solutions that do not collaborate, then we have an unstable situation. Okay? How can we recognize it? That's a good question. Let's have a look at our situation over here. So we go back to Maple. And I have a little code here. I focused on the stationary solution 1,1 or equilibrium 1,1. And what do we have here? Well, we can see the stationary solution as dark blue curve, or rather straight line, or a rod in 3D. And I started with 1, 2, 3 different situations, 4 different situations. When I situate it like that, now you can see exactly the starting points. The green one, the whatever, gold one, and so on. Or perhaps it's the red one? Yeah, I guess it's the red one. Okay, how do I twist it back? This way. So, now the time is going to the right. And we can see that those 3D solutions are sort of circling around in space, but they do not seem to be going back to my stationary solution. Okay? This is really bad. I would be very pessimistic based on this picture. So I would say that the stationary solution 1,1 is unstable based on my situation, but there are problems. First of all, perhaps if I go in time farther to the right, then those interesting curves will go back, or perhaps not, I don't know. You see, This system is unsolvable. So what do you see over here? These are numerical solutions. So I cannot use analysis to say what happens when time goes to infinity. I cannot just calculate a limit or whatever. The second problem is, imagine that these curves will be actually going to my stationary solution. But that's just 4 of them. But I need all solutions on a neighborhood. Can I check on all solutions numerically? The answer is no, because I have to calculate each of them one by one using some numerical procedure. So the idea is quite clear, but we need to get some tools or some new insight into what's happening so that we can really judge reliably whether our stationary solutions are or are not stable. And for that, we will start with something that we know really well, which is linear systems. Here we have a very nice linear system, which is actually homogeneous, which is great. We know how such systems work. And I'm asking, are there any stationary solutions? So I'm actually asking for the right-hand side to be 0 as a vector. And that's something that we do in linear algebra, and we know that there is at least one solution, namely the trivial solution. All zeros. Definitely solves my system. So that's a stationary solution, or equilibrium, depending how you look at it. Of course, there could be other stationary solutions, because if the matrix A is singular, then there is in fact infinitely many of them. But people really do not worry about it very much, because in applications, the matrix A is typically regular. And moreover, even if there are some other stationary solutions, we generally cannot really say very much about them. So people focus on the trivial stationary solution. And now we ask the key question, is it stable or not? Well, we have this stationary solution, which is actually just the t-axis now. Everything is 0, y1 and y2, throughout all the times. And stability means that when I look at nearby solutions, they tend to this stationary solution in a limit. So, why not the trivial solution is stable if solutions go to 0? But now here comes a trick. I'm not going to say for nearby solutions. I'm going to say for all solutions. How can we afford to replace one condition with another? I claim that actually these two conditions work exactly the same way for homogeneous linear systems. First of all, if all solutions go to 0, then also nearby solutions go to 0 automatically. So in one direction, the correspondence is quite clear. Let's have a look at the other direction. Let's imagine that we find that our trivial solution is stable, and therefore, according to definition, all the nearby solutions go to 0 in limit at infinity. Now, what happens to other solutions, those that are not nearby? There's a solution sitting over here, let's say, and it's too far, perhaps. Well, our system is homogeneous, and therefore solutions form a linear space, which means that if I take this solution and divide it by perhaps 100, I will get a solution which is near the origin. So it's small enough. And if it's not small enough, I divide by 1,000, by, you can imagine how it goes. So from this solution, I pass to a, okay, let me give it a name. I pass to 1 over 100, let's say, y. And because it's a nearby solution, and my trivial solution is stable, then this nearby solution must converge to 0. But if this solution converges to 0, then multiplying it by 100 still creates a solution which goes to 0. So this linearity business is very useful because the behavior around the origin translates automatically or extends automatically to behavior everywhere. So I don't have to worry about some neighborhoods. I simply look at all solutions and ask, do they go to 0? That's a much easier situation to handle. Moreover, going to 0 can be actually translated like that. I can ask whether the magnitude of my solution goes to 0 as a number for all solutions. And this is where it gets interesting. First of all, when you have a homogeneous linear system, you can simply write down the solution, look at it, look at the formulas, and ask, do all of them, all possible solutions, go to zero or not? And that's a question that you can usually answer. No problem there. And we actually did it before. But let's get more sophisticated. What do we know about solutions? Well, all solutions of such a system are just a combination of some fundamental systems. So we have a fundamental system which consists of some vectors, let's say y1 through yn. And then we have a general solution, which is just a combination of these guys. Now, in order for the trivial solution to be stable, we need all solutions to go to zero, which means that also these guys in the fundamental system have to go to zero because there are solutions. They are solutions by themselves. Conversely, if all the functions, all the vector functions in my fundamental system go to zero at infinity, then their linear combination will be also going to zero. So this whole problem reduces to just my fundamental system. Do these guys go to zero or not? Let's have a look at them. A typical vector function in my fundamental system looks like this. It's some vector and exponential, where lambda I is obviously an eigenvalue, and vi is an eigenvector corresponding to lambda I. Now, when I ask about the magnitude, I will actually have to find the magnitude of the eigenvector, because this is just a number, it can be pulled out. And then, when we ask about the magnitude of the exponential, we find that it does not depend on lambda as such, only on its real part. Because the imaginary part gives rise to cosines and sines, when we go to the real imaginary part, we don't have to really worry about it, because the absolute value or the magnitude takes care of it, and the magnitude of e to I something is always 1, period. So this is how the situation looks like for a typical vector in our fundamental system. If you are worried a little bit about this complex part, just imagine that lambda I is real for a second. Now, we want these vectors to go to zero. When does it happen? Well, this is a constant eigenvector. This doesn't change. T goes to infinity. If this exponential is to go to zero, then we need to require that lambda, or its real part, is negative. Otherwise, it will not go to zero. And we need this for all vectors in our fundamental system. Now, let's put it together properly. If your lambda is real, then you can ignore this real part, and you're simply looking at exponential, and the exponential goes to zero if and only if the coefficient is negative. So far, so good. What if lambda is complex? Then we know that we are looking at real part and imaginary part, and it gets a little bit complicated because this vector may have some complex, it will have some complex components. Things will get a little bit complicated. But anyway, if we want our fundamental system to go to zero, then the real part must go to zero, the imaginary part must go to zero, and therefore this complex exponential must go to zero, and we are here, exactly in this part. So what we did was actually correct, even if we take into account this complicated situation with passing to real imaginary part and so on. The last problem appears if lambda is a real or complex eigenvalue with higher multiplicity. Then the solution is actually some combination of vectors, and also there can be some power of our variable, let's say power m. And the question is, what happens then? And again, we can take the norm, ask how large this is, and when we do so, we find that we are actually looking at the power times the exponential, again with real part of the eigenvalue in it. Now, what is the limit at infinity? We know this from calculus. Exponentials are dominant. So the limit is simply decided by what happens to the exponential. If the exponential goes to infinity, so does the whole thing. If it goes to 0, so does the whole thing. So essentially, we get the same criterion. If you want to go to 0, we simply need this coefficient to be negative, period. And it works for higher multiplicity, for complex. It works always for all eigenvalues. And that's a general theorem which we can look at over here. And it says, if you have a homogeneous linear system with constant coefficients, then the trivial solution is automatically stable or asymptotically stable exactly if all the eigenvalues have negative real parts. And the proof actually can be done based on the analysis that we did over here. You just do it a little bit more carefully. If just one eigenvalue refuses to cooperate, then you've got an unstable situation, unstable stationary solution. So when you're investigating stability, you can go for it intuitively. You find your general solution and you ask, does it always go to 0 for all possible choices of A, B, C, whatever coefficients you're using? So on intuitive level, you can do it like that. Or you can simply look at your matrix, find the eigenvalues, and just by looking at eigenvalues, you know exactly what to expect. You know the stability of your trivial solution. And that's very handy, and it will come handy later on after we pass to more complicated situations. Before we do that, let me just recall something from past lectures, because we already investigated some systems, and one of them, the very first system that we had eigenvalues 1 and 3, and therefore the trivial solution should be unstable. And what I did, I actually plotted some solutions. And you can see them here. The trivial solution is dark blue, dark navy. It's the t-axis. And actually, it's not visible all that plainly, but OK. And the green curves, that's the solutions. And as you can see, they go away. So that's exactly what you can expect when your eigenvalues are positive, both of them. OK. The next example that we had was the complex case, when you hit cosines and sines and things like that. And this gets really interesting. So this is the situation when you have complex eigenvalues. The solutions, they look like that. It's very nice, isn't it? And let's say that we look at the gold one. Actually, that's the official name of the color, gold one. When I look at it from this point of view, I can see just one of the unknown functions. And as you can see, it's, well, in this way, it's negative cosine, but I have it upside down, actually, when I'm looking at the y2 axis. So let me just rotate it. Now the y2 axis is seen properly. So y2 is just the cosine function. And we can see it over here. Yeah, it's cosine. And then I rotate it so that I can see the y1 axis. So the y1 component of my solution is the sine function. And we can see it nicely. Okay? And the other solutions, they are just sine which is shifted. For y1, for y2, it would be cosine which is shifted. So this is how things look like when we have a nice complex situation. And by the way, since the solutions are circling around the trivial solution, of course the trivial solution is unstable. And again, that's because the real parts were not negative. In this case, if you remember, the eigenvalues were plus or minus 2i. So that's a pure imaginary number where the real part is 0. And, well, 0 does not satisfy this condition. So we have instability. And finally, we had an example where lambda was negative 2, but it was of higher multiplicity, which is exactly this case. So when lambda is negative 2, double multiplicity, according to our observations, we should see stability. So again, I plotted some solutions just so that we can see what's happening. And as you can see, those solutions are approaching the trivial solution very nicely. And there are some, when you look at the y2 and y1, you will see exponentials. So that's exponentials for y2, and that's exponentials for y1. Very nice. Okay. So much for homogeneous linear systems. And let me just show you one application. I got this equation from my friends working in electrical circuits theory. And they tell me that it describes circuits that feature resistors, capacitors, and coils, essentially. I will talk about it more in my lecture on applications. Right now, we are not really worried about that. We are worried about the fact that this is a linear differential equation, and it's homogeneous, and therefore it does have a trivial solution. Is it stable? That's a good question. Now, just out of curiosity, I stands for the current which is flowing through the circuit. So when you have a circuit, some, those little bugs with little legs which are soldered onto a plate, and there are some wires connecting them, whatever, perhaps some battery or whatever. If you have such an electrical circuit, when it's switched off, there is no current happening, and yeah, it's okay. That's definitely one of the solutions. But what happens if you put some electrical energy into it, let's say some charge on the capacitor, whatever, and there is some current circulating around? What happens when you go to infinity? That's a good question. Stability of such a solution means that all the situation in all possible settings for the system, eventually the current goes to zero. Which is interesting. So does it happen? Question mark. Is it stable? Well, we do not have really the notion of stability, or we didn't look at it for linear differential equations of higher order. So what do? I change it into a system. I take the derivative of I and give it some name. Derivative of I could be, let's say, J. I suspect that people from physics, from electrical circuits theory, they would have a different name perhaps for it and perhaps some story about it. I'm a mathematician, I do not care. Derivative of I is J, good for me. Okay, J prime plus R over L J plus 1 over LC I is 0. And let's rewrite it. So the proper form is I derivative is J, J derivative is minus 1 over LCI minus R over L J. That's the system that I'm looking at, and it has the obvious trivial solution, I is 0, J is 0. How about stability? Well, for that I have to look at the matrix, first of all, and the matrix of the system is 0, 1, minus 1 over LC, and minus R over L. And now I look for the eigenvalues. So I'm checking on the determinant of the matrix minus lambda 1 minus 1 over LC minus R over L minus lambda. How much is it? I have to take the product here, I pull out all the minuses, and it becomes lambda squared plus R over L lambda, and I will subtract this product, and it ends up with plus sign. And I'm asking, could this be 0? Well, let's see. We have a formula for lambda. In the denominator, twice this coefficient, which is just 1, so it's 2 over here. This guy is put here with minus, plus or minus square root of, do I care? No, I don't. There is something here. And all I care about is the real part. That's the point. When I'm asking about stability, I just look at the real part of my lambdas. What do I see? The real part is over here. It's minus R over 2L. Now R is the resistance or whatever. These are physical constants. The important thing is they can never be negative. They are both positive, R and L, or perhaps 0 for R. So I know for sure that this is less than or equal to 0. And now there are two distinct cases. When R is 0, then the trivial solution is unstable. So the current can flow indefinitely. R is the resistance. So if there is no resistor in the circuit, I put in some charge, some electrical energy, and it will just be going around essentially forever. However, if I do put some resistor into my circuit, then the resistor will be sucking out the energy of the system and it will disappear. In all the situations, the current will eventually go to 0 in limit. So the trivial stationary solution is stable. Wow, that was easy, wasn't it? I mean, it's nice to have some theory and some understanding of stability. So that's this nice example. Well, it was going really well. So let's extend it. How about non-homogeneous systems? That's a good question. Derivative of y is ay plus b. Now, when we looked at these systems in general, we also included the possibility that the right-hand side b involves the variable. But here it will turn out right away that this is not a good idea. Why? Okay, I'm looking for a stationary solution. Stationary solution must have 0 here. So, ay plus b is 0. That's the equation I'm looking at. And let's just imagine for a second that there's also the variable t present in the right-hand side b. If I do find a stationary solution, then b will be minus a y naught. Now, a stationary solution is a constant vector. A is a constant matrix. This is a constant vector, and therefore b cannot involve any t in it. In other words, when you see a non-homogeneous linear system where the matrix is constant and the b, the right-hand sides, are not constant, then there is no stationary solution. Right away, you know it. So if you want a stationary solution, you want b to be a vector of numbers. And then if A is a regular matrix, then definitely there is some solution. And we have it. This is our stationary solution. What if A is singular? Then there could be infinitely many stationary solutions or perhaps no stationary solution. But notice, if A is singular, then one of its eigenvalues must be 0. And therefore, if there is a stationary solution, then it's automatically unstable. And we are done. So that's nice. Anyway, let's go back to our nice situation. A is a regular matrix. We found a stationary solution, and we can take it as the particular solution. So the general solution has the form y is equal to y naught plus yh. Now, when is our stationary solution stable? Well, it is stable if all nearby solutions go to it. But now, all the nearby solutions look like this. We have y naught, that's our stationary solution, and some solution of the homogeneous system. And now we see easily that we have stability for y naught if all the yh's go to 0. So this is exactly what we were investigating for homogeneous systems, and we know what to do. We look at the matrix A, we find the eigenvalues, and we want the real part of all the eigenvalues to be negative. The same criterion, the same theorem also applies to non-homogeneous systems where the right-hand side is constant. That's very nice. Okay, can we extend this to even more general situations, for instance, like this one? The answer is, well, not directly, because there is no matrix A. So without matrix A, we don't have any eigenvalues, whatever. But perhaps we can take inspiration from the pictures, from the ideas. It's possible, but for that, we actually need a slightly different point of view at the solutions. We saw the solutions as individual functions. That was nice. We saw them as two-dimensional, whatever dimensional curves. That was also nice. But now the time comes to try yet another point of view.